Hello students, welcome to the class. So in the previous class, we have discussed regarding the theories of acids and bases. And the last thing what we had discussed was the limitation of Lewis theory of acids and bases. And what is it? What is the limitation? It does not explain the relative strength of acids and bases, right? So what is that relative strength? We'll understand it by ionization of acids and bases. So strength of the acid or a base, it is determined with the extent of ionization in the aqueous solution. That means how does it ionize in the aqueous solution? So if I take here, I can say that we use the common factor what we use is K. In practice, Ka is used to define the strength of only those acids that are weaker than H3O plus. So this is dissociation of an acid and Kb is dissociation of a base. This is what we use. Okay. Strength of the base you can say. So for two acids, so I'll consider the acids we can define dissociation constants of the acids which are weaker than H3O plus or bases which are weaker than OH minus. Okay, therefore, these are the dissociation constants of weak acid and weak base and weak bases. Okay, because for strong acids and strong bases, the dissociation is complete. Yes, we say degree of dissociation is equals to 1. Therefore, if I consider for two weak acids, say HA1 and HA2, these are the two weak acids. Why I'm calling them acids? Because they have H plus ions. The dissociation constants will be Ka1 and Ka2. Okay. So acid strength, if I want to compare, strength of first acid to the strength of second acid, Ha2, will be what? It will be equal to, yes, it is solved, the root of dissociation constant of acid 1 to the dissociation constant of acid 2. This is solved actually. Yes. Similarly, if you want to compare the relative strengths, yes, what it is? Relative strength, comparison of relative strength, which is more acidic, which is more basic. So relative strength of two bases. Two bases. I can represent two bases as BOH1, yes, and BOH2. So if I want to calculate the strength, the relative strength of BOH1, OH because OH minus is there, therefore it is a base. Strength of is 2, strength of second base, it will be equal to what? It will be equal to root of dissociation constant of base 1 to the dissociation constant of base. We write it as a subscript here. Dissociation constant of base 2. Base 2. Yes. So this is how we find the strengths of acids and bases. With this, we have few examples also. If you want to calculate these dissociation strengths, relative strengths of hydrides, yes, I can tell you, please do remember this, which will help us. Not simply sitting and worrying about what are the relative strengths. You can directly remember this. Acidic strength increases. Yes. So I can say here, acidic strength, it increases with increase in electronegativity of element which is attached to hydrogen. Yes. So which is most acidic, I can say, according to this. So acidic strength increases with the increase in electronegativity. So if you consider halogens, HF becomes more acidic. Then comes HOH because oxygen is next more acidic. Then comes nitrogen, which is third most electronegative. Then comes carbon. Yes. So this is how I write. Even if you see HCl, then comes H2S, then comes PH3, phosphine, then comes SiH4. So this is about hydrides. The second one is about oxyacids. Now, what are oxyacids? Oxyacids are those in which the oxygen is attached to hydrogen. Oxygen is attached to hydrogen. The removed hydrogen should be attached to oxygen. So among oxyacids of same type formed between elements, acidic nature, or you can say acidic strength, increases with increase in electronegativity. Therefore, here, in case of oxyacids, I can say HOI is less acidic than HOBr, which is less acidic than HOCl, or HO or HiO4 is less acidic than HBrO4, which is less acidic than HClO4. So HClO4 is more acidic. If the oxyacids are attached to same element, say here I have taken iodine, bromine, chlorine. If they are attached to same element, then acidic nature increases if same element acidic strength increases with increase in oxidation number. I can show you. See, HOCl is less acidic than HClO2, which is less acidic than HClO3, which is less acidic than HClO4. Or I can say H2SO3 is less acidic than H2SO4. It is less acidic than H2SO4. The reason why I'm saying this is, if you look here, the oxidation states, if you look at the oxidation states of chlorine, here it is +1, here it is +2, I'm sorry, it is +3 here, you can calculate. Here it is +5, here it is +7. Understanding? So as oxidation number increases, the acidic strength increases in case of oxyacids. Yes, so this is fixed. Yes, this is fixed here. Then relative strengths of inorganic bases also you can calculate. Relative strengths of inorganic bases. Like for example, NH3 is more basic than H2O, which is more basic than HF. Yes, this is calculated how is basicity of the compound decreases with increase in electronegativity. Yes, so with the decrease in electronegativity, and second one, larger the size of atom, having unpaired electrons, So I can say here with second point, F minus is more, then comes Cl minus, then comes Br minus, then comes I minus. Yes, so this is how we explain relative strength of inorganic acids. Even you can explain the relative strength of organic bases also. Yes, so this is about relative strengths of acids and bases. With this relative strength of acids and bases, we can understand so many things. And one is that, which was not being explained by most of the theories, acid-base neutralization and salt formation, correct? Salt formation. So when we speak about this concept, the reaction between an acid and a base to produce salt and water is called neutralization reaction. It is termed as neutralization reaction. The process of neutralization does not produce the resulting solution always neutral. Yes, it forms a neutral salt, we say, but always it is not neutral only. No doubt it involves the interaction of H plus and OH minus ions. Now it depends. The what you can say, strength of this salt, whether it is acidic, it is basic, it is neutral, that depends upon the conditions. So now let us try to understand about these salts. Correct? So here we have salts are regarded as the compounds made up of positive and negative ions. So it has positive ions and negative ions. If you take an example, let me share you with an example. Let me say I have HCl plus NaOH gives me NaCl and water. Correct? Is that right? Okay. What is this HCl? it is acid. NaOH is base. It is giving me salt and water. Neutralization reaction. Is that right? Okay. Please observe, students, properly. A acid has H plus ion and Cl minus ion. Base has Na plus ion and OH minus ion. Salt has Na plus ion and Cl minus ion. Correct? So salts are made up of positive and negative ions. Positive ions come from where? Positive ions come from base. Correct? Therefore, the positive ion present in salt, it is also called basic radical. What it is also called? Basic radical. Or you can call it as cation. Correct? Basic radical or cation. Negative ion comes from where? Negative ion comes from acid. This is true always. Therefore, it is also called acid ion, acid radical. Or you can call it as anion. You can call it as anion. Always it is for salts. So positive ion is a part of a base and negative ion is a part of an acid. Yes. Salts therefore are what? They are ionic compounds. What they are? Ionic compounds. The salts can be further classified. Yes, you can further classify these salts as simple salts. We have simple salts. Then we have double salts. Then we have complex salts. And we have mixed salts. Mixed salts. Yes. So what are simple salts? Simple salts. So 4 types of salts we have. Simple salts means the salts formed by interaction between an acid and a base is called simple salt. In this again, we have 3 types of salts. One is normal salts. Now, what do we mean by normal salts? The salts formed by loss of all possible protons are called normal salts. Such a salt does not contain either replaceable hydrogen or hydroxyl ion. Like for example, you take NaCl. It does not have replaceable hydrogen or OH minus ion. You take NaNO3. Does not have H plus or OH minus ion. You take K2SO4. These are what? These are normal salts. Second type of salts are, yes, they do not contain any replaceable hydrogens. Second salts are acidic salts. Okay. So salts formed by incomplete neutralization. Formed by incomplete neutralization of polybasic acids are called acidic salts. Yes, they contain one or more replaceable hydrogens. Like for example, NaHCO3. Or you can take NaHSO4. Or you can take NaH2PO4. So they contain replaceable hydrogens. Third type of salts are basic salts. Okay. These are what? These are formed by incomplete neutralization of polyacidic bases. These are incomplete neutralization of polybasic acids. Okay. Polybasic acids. And these are formed by incomplete neutralization of polyacidic bases. Polyacidic bases. Yes. And here we take the examples of, it contains OH minus ion, ZnOHCl. Yes. Then you have MgOHCl. Then FeOH twice Cl. So it contains OH minus ions. Correct. So these are type simple salts. First type, that is simple salts. We have normal salts, we have acidic salts, and we have basic salts. The next type of salts is double salts. Now, what are these double salts? Okay. Double salts means the addition compounds formed by combination of 2 simple salts are termed as double salts. They are stable only in solid state. Yes, they are, double salts are what? They are addition compounds. Addition compounds formed by the combination of 2 or more single salts, simple salts. For example, ferrous ammonium sulfate. Ferrous ammonium sulfate is an example for double salt. You have potash alum. potash alum, all alums and other alums you can say, ALUMS. Yes, these are all examples for double salts. Then we have complex salts. What are complex salts? Yes, complex salts are those which are formed by combination of simple salts or molecular compounds. So here, double salts, they are stable only in solid state. Yes, they are stable only in solid state. Whereas these complex salts, they are stable both in solid as well as liquid state. Yes, solid as well as liquid state. So they are combination of two or more simple or molecular compounds. Like for example you can take when ferrous sulfate combines with KCN, it gives me, yes, I'll write it here. It gives me K4 Fe CN6. So 6 KCN. Yes, plus K2SO4. This is called complex salt. Yes, or you can call it as coordination compound also. Yes, and the last type is, it is mixed salts. Now, what do we mean by these mixed salts? The salts which furnish more than one cation or one anion when dissolved in water are called mixed salts. So, which have more than one cation or anion are called what? They are called mixed salts. Example, you can take CaOCl and then Cl. So it contains Ca plus 2 ion, OCl is one ion, Cl is another ion. Then you can take NaSO4K. So this is example for mixed ion. Yes. Then the next very important concept is ionic product of water. Okay. So pure water is a weak electrolyte. When we speak about pure water, it is weak electrolyte. That means it hardly conducts electricity. Okay. So and undergoes self-ionization to a small extent. The product of, yes, very important, the product of concentration of H plus and OH minus ions, H plus and OH minus ions in water at a particular temperature, is known as ionic product of water, and it is denoted by Kw. So Kw stands for what? It stands for ionic product of water. Yes, the product of concentrations of H plus ions and OH minus ions is at a particular temperature is called ionic product of water. How do we explain it? See, we know that water self-ionizes to give H plus and OH minus ions. Yes, and delta H is 57.3 kilojoules per mole. Okay. If you write dissociation constant according to, see, equilibrium constant here. If you want to represent the equilibrium constant, how do you write the equilibrium constant? K is equal to Kc, you will say, yes, I will keep it as K. Okay, let me take it as Kc only to make you all understand. First, we write the ratio of, right? Product of concentration of the products into OH minus divided by product of concentration of the reactants, but here I have only water. Yes. So this is how we write. Take H2O concentration that side. What it becomes? It becomes Kc, equilibrium constant of nothing but what? Molar concentration of water is equal to what? It is equal to concentration, molar concentration of H plus into molar concentration of OH minus. Kc into molar concentration can be written as Kw. Therefore, Kw is equal to molar concentration of H plus ion into molar concentration of OH minus ion. H plus ion and OH minus ion. So the value of Kw, what is Kw? It is ionic product of water. Yes. So this value of Kw, it increases with increase in temperature. With increase in temperature. That is, concentration of H plus and OH minus ions increases with the temperature. Yes. Specifically, value of Kw at 25 degrees Celsius. At 25 degrees Celsius is 10 raised to minus 14. Yes, sometimes we say, in some books they have given 1 into 10 raised to, doesn't make difference. 10 raised to minus 14 moles per liter. Yes, or in some books it is given 1 into 10 raised to minus 14 moles per liter. Yes, this is the value of Kw, ionic product of water. So from this, what all information we can get, you just see. Since pure water is neutral, pure water if you take, it is neutral. Yes. So since pure water is neutral, okay, since it is neutral, H plus ion concentration must be equal to OH minus. So water is equal to what? H plus and OH minus ions. Since it is neutral, how many concentrations of H plus ion I have? The concentration of H plus ion should be equal to the concentration of OH minus ion. Correct? So if I say H plus ion concentration is equal to OH minus ion concentration is equal to X. Let me take it as X. Multiplied H plus ion concentration into OH minus ion concentration is equal to what? Into. So it becomes X square. And that is equal to what? That is equal to ionic product of water. Correct? Yes. Therefore, X square is equal to 1 into 10 raised to minus 14. Therefore, what is X equal to? X will be equal to 10 raised to minus 7 molarity, moles per liter. Therefore, if Kw of water, ionic product of water is 1 into 10 raised to minus 14 molarity, H plus ion concentration is 1 into 10 raised to minus 7 molarity, and OH minus ion concentration is 1 into 10 raised to minus 7 molarity. Multiply H plus and OH minus, you will get this value. 10 raised to minus 14 moles per liter. So this shows that at 25 degrees Celsius, in 1 liter, yes, in 1 liter, only 10 raised to minus 7 moles of water is in ionic form. Yes, out of totally approximated 55.5. So moles of water are in ionic form. They are in ionic form. Is that right? Therefore, with this explanation, can I conclude saying when H plus ion concentration is equal to OH minus ion concentration, it is neutral. That is 10 raised to minus 7. So I call it as neutral. Correct? Okay, let me take a better new slide. H plus ion concentration is equal to OH minus ion concentration. That will be equal to what? 10 raised to minus 7. Because when you multiply both of them, it becomes 10 raised to minus 14. That is ionic product of water. And I call it as what? Neutral. Correct? Okay. If H plus ion concentration is more than OH minus ion concentration, then the solution is what? Then the solution is acidic. It is acidic. If H plus ion concentration is less than OH minus ion concentration, then the solution is basic. It is basic. Clear with this? So this is about the ionic product of water. Yes. Pure water is a weak electrolyte. The product of concentrations of H plus ions and OH minus ions in water at a particular temperature is called what? Ionic product of water. Yes, if you see dissociation, write the equilibrium constant, we get this. Substitute all the values. Then we come to value of Kw increases with increasing temperature. At 25 degrees Celsius, it is 10 raised to minus 14 moles per liter, or you can say 1 into 10 raised to minus 14 molarity. So since pure water is neutral, how many H plus, the concentration of H plus ion should be equal to the concentration of OH minus. If you consider it as X, ionic product of water is what? X square, because both the ions multiplied. X, if X square is 1 into 10 raised to minus 14, then what will be X? It will be 10 raised to minus 7. So ionic product of water is 1 into 10 raised to minus 14 molarity. H plus ion concentration is 1 into 10 raised to minus 7 molarity. OH minus ion concentration is 1 into 10 raised to minus 7 molarity. Yes. So at 25 degrees Celsius in 1 liter, 10 raised to minus 7 moles exist in ionic form other than 55.5 moles. Yes. Then further we come to the conclusion that H plus ion concentration, if both H plus and OH minus ion concentrations are equal, it will be equal to 10 raised to minus 7. And that is said to be neutral solution. If H plus ion concentration is more than OH minus ion concentration, solution is acidic. If H plus ion concentration is less than OH minus ion concentration, solution is basic. So with this, a scientist by name Sorensen, yes, he was a Danish biochemist rather than scientist. He developed a scale to measure acidity. Yes, he developed a scale to measure what? To measure acidity. Yes, in terms of concentration of H plus ions. In terms of concentration of H plus ions in the solution. So as defined by him, pH of the solution is, pH of a solution is, he defined it as negative logarithm of negative logarithm to the base 10, very important, to the base 10 of concentration of H plus ions, which it contains. Yes. So mathematically, I can represent it as pH is nothing but negative logarithm to the base 10 concentration of H plus ions. Yes. I can write it like this, or even you can write pH is equal to log of, remove the negativity sign, 1 divided by concentration of H plus ions. Yes. So just pH indicates the hydrogen ion concentration. POH represents what? Hydroxyl ions. So POH is equal to what? It is equal to negative logarithm to the base 10 of OH minus ion concentration, or POH is equal to log to the base 10, 1 divided by OH minus ion concentration. Yes. So you consider the relationship of ionic product of water. What it says? H plus into OH minus is equal to what? Kw. And what is Kw equal to? 1 into 10 raised to minus 14 molarity. Correct? Take the log on both the sides. So how do we write it? Log to the base 10 H plus ion concentration plus log to the base 10 OH minus ion concentration is equal to log to the base 10 Kw, that is equal to log to the base 10 1 into 10 raised to minus 14. Yes? Yes? Okay. Now what you do? Minus the signs. Everywhere you take minus. So minus log to the base 10 of H plus ion concentration minus log to the base 10 of OH minus ion concentration is equal to minus log to the base 10 of Kw, that is equal to minus log to the base 10 of 1 into 10 raised to minus 14. Now what is this minus log to the base 10 of H plus means what? pH. Correct? pH plus minus log to the base 10, I can write this like this. It is written actually like this. Plus minus log. Okay. Okay. Plus minus log to the base 10 of OH minus means what? It is POH. Correct? Is equal to minus log to the base 10. I can write it as PKW. That is equal to minus log 1 into 10 raised to minus 14 becomes what? It becomes 14. Yes. So this is the value of, this is the relationship between pH and POH. relationship between pH and pOH. pH plus pOH is equal to pKW, and that is equal to 14. Yes. So here we understand many concepts. H plus ion concentration is equal to OH minus ion concentration, that is equal to 10 raised to minus 7. Kw value is what? It is 1 into 10 raised to minus 14 molarity. H plus ion concentration is what? 1 into 10 raised to minus 7 molarity. OH minus ion concentration is what? 1 into 10 raised to minus 7 molarity. What is pH value for neutral water, neutral solution? For neutral solution, pH is 7. What is pOH value for neutral solution? It is 7. What is pKW value for neutral solution? It is 14. Yes. So if I make a scale here, if I make a, what you say, a diagram, or sorry, a tabular column for say acidic solution, say for a neutral solution, and basic solution. Basic solution. So here what criteria I'm going to take is, I'm going to talk about H plus ion concentration. Then we will say about OH minus ion concentration. Then we will talk about pH and pOH. Correct? Yes. So let me take a line here. To distinguish. So let me say I have here. Okay. So let me say I've taken it. So here also better we will make a diagram itself. It would be better if we take the tabular column, right? Is that right? Okay, fine. So here H plus ion concentration for neutral solution, it is 10 raised to minus 7. For acidic, it is more than 10 raised to minus 7. For basic, it is less than 10 raised to minus 7. Correct? OH minus ion concentration. For neutral, it is 10 raised to minus 7. For acidic, it is less than 10 raised to minus 7. For basic, it is more than 10 raised to minus 7. Okay. pH. For neutral solution, it is 7. For acidic, it is less than 7 because 10 raised to minus 7. Yes. For acidic, it is less than 7. For basic solution, it is more than 7. pOH, for neutral, it is 7. For acidic, it is more than 7. For basic, it is less than 7. So this is the scale. Yes, this is the scale. You can look at the examples also. For example, if you see gastric juice, the juices present in the stomach, they are called gastric juice. The pH is 1.4. For lemon juice, yes, what lemon juice we take? A very good antioxidant, right? Its pH is 2.1. Then vinegar, acetic acid, yes, its pH is 2.9. Then we have soft drinks. The soft drinks what we take? The soft drinks, they have the pH of around 3, acidic pH. Then beer, what the people have, yes, it has the pH of 4.5. Black coffee, yes, many of them take it in the CCDs, right? Black coffee, the pH is around 5. Cow's milk, what do you expect? Cow's milk, the pH is around 6.5. It is also acidic. Rainwater, normal rainwater, the pH is around 5.6. Yes, 5.6. Then we have pure water. If you take pure water, you know that it is neutral. Therefore, pH is what? It is 7. Human saliva, because of which all the food gets dissolved, it is also 7. Blood plasma, what is the pH of our blood? It is 7.4. Yes. Tears, yes, what we get? It is also around 7.4. Egg has got the pH of 7.8. Yes, so these are all the pH of different materials which are being used. So with all these useful things, well, there are certain limitations of this pH also. Yeah. So pH scale. Hydrogen ion concentration are measured as the number of gram ions of hydrogen present per liter of the solution. Since these concentrations are usually small, the concentration is generally expressed as pH of the solution. pH being the logarithm of reciprocal of hydrogen ion concentration. Yes. Okay. So when we speak about acids and all, as I said, it faces certain limitations. The limitations what it faces is pH value of the solution. Yes, pH of value of the solution does not give us immediate idea of relative strengths of solutions. A solution of pH 1 has hydrogen ion concentrations 100 times than the solution of pH 3, not 3 times, correct? So it does not give us the proper idea. Then a pH value 0 is obtained in one normal solution of strong acid. That is also not correct. Yes. Therefore, we go for pK values. Rather than pH, we go for pK values. So what are these pK values? P stands for negative logarithm. Just as H plus and OH minus ions have a range over many negative powers of 10, it is convenient to express them as pH and pOH. Similarly, we express for acids and bases pK values. So pK is what? pK value is negative logarithm of dissociation constant. So for acid, I represent it as pKa. It is equal to what? Negative logarithm of Ka, dissociation constant of weak acid. pKb is what? Negative logarithm of Kb. So just now we had seen as Ka value increases, the strength of acid increases. But what is pK? Negative log. Therefore, I can say as pK value increases, the acid becomes less strengthened. Yes. Or I can say as Ka value increases or pKa value decreases, strength of acid increases. So for increasing acidic strength, either Ka value must be high or pKa value must be low. Yes. So weaker acids, if you see, weaker acids have what? Have higher pKa values. Correct? They have higher pKa values. Similarly, weaker bases have higher pKb values. Yes. So as Ka value increases or pKa value decreases, the strength of acids increases. Yes. So for any conjugate acid-base pair, I can say Ka into Kb is equal to what? Is equal to Kw. Or pKa plus pKb is equal to pKw. Yes, please do remember for any conjugate acid-base pair. For any conjugate acid-base pair, this holds good. And that is equal to what? That is equal to 14. It remains fixed. It remains fixed. Is that clear? Okay. So this is small explanation regarding H plus and OH minus ions. Di and polybasic acids. Acids which contain more than one ionizable proton per molecule are di or polybasic acids or polyprotic acids. Oxalic acid has got 2 hydrogens. So it is dibasic. Sulfuric acid has got 2 hydrogens. So it is dibasic. Phosphoric acid, H3PO4, has got 3 hydrogens. Therefore, it is tribasic, or you can say polybasic. The ionization reactions for a dibasic acid is represented as C, H2X, dibasic. So H plus plus HX minus. HX minus, H plus plus X2 minus. Their equilibrium constants can be written as. So this is first acid and this is second acid. Therefore, I can say Ka1, dissociation constant of acid, weak acid, first one. H plus ion concentration into HX ion concentration divided by H2X. Ka2, H plus ion concentration into X2 minus ion concentration divided by HX minus. So Ka1, Ka2 are first and second ionization constants respectively. For a dibasic acid, Ka1 is always greater than Ka2. Okay. Now, what are the factors which affect the acidic strength? When the strength of HA bond decreases, yes, the energy required to break the bond decreases. HA becomes a stronger acid. When you require to break the bond, when you require less energy, it becomes very strong acid. Yes, as the size of A increases down the group, HA bond strength decreases and so the acidic strength increases. Okay, in a period as electronegativity of A increases, strength of acid also increases. And here you have, see, as size increases, acidic strength increases. Correct? Then electronegativity of A increases, acidic strength also increases. Then moving to the next one, that is common ion effect. What do we mean by common ion effect? Yes, very important concept. Fine. So we are common ion effect, and here we have buffer solution. Okay. If in an aqueous solution of a weak electrolyte, a strong electrolyte is added having a common ion with the weak electrolyte, then the dissociation of the weak electrolyte is decreased or suppressed. It is decreased or suppressed. The effect by which dissociation constant decreases is called as common ion effect. See, they have given an example. Let us try to understand the example. Okay, fine. So common ion effect. See, what do we mean by this is the degree of dissociation of a weak electrolyte is suppressed by the addition of strong electrolyte containing common ion. For example, let us take dissociation of weak electrolyte. Acetic acid is a weak electrolyte, CH3COH. It is weak acid. It dissociates partially, therefore there exists equilibrium, right? We get CH3COO minus plus H plus. Yes. So, acetic acid being a weak electrolyte, its ionization is suppressed in the presence of strong acid or a strong salt like sodium acetate. Suppose I will take a salt. I will add to this a salt, sodium acetate. It is a strong salt. What it is? It is a strong salt. So it will ionize completely and give me what? CH3COO minus plus Na plus. So it will ionize completely to give me acetate ions and sodium ions. So what happened here? Can you see these common ions? So the degree of dissociation of weak electrolyte is suppressed by the addition of a strong electrolyte having common ion. Yes. So as the result, what happens? The concentration of ion of weak electrolyte, which is not common, it is decreased. Yes. You can take one more example. This is for acid. I can take weak base. NH4OH is a weak base. It will dissociate partially. It will give me NH4 plus OH minus. If I add a salt of strong acid, say NH4Cl, it will dissociate completely. So it will give me what? It will give me NH4 plus Cl minus. So here what I have got? I've got common ion. So this is called what? This is called common ion effect. It is called as common ion effect. And here what example is given? Let us see. Okay. Same example. Aqueous solution of CH3COH. A small amount of CH3CONa, that is strong electrolyte, has been added. Due to presence of common CH3CO minus ions, they are called acetate ions, equilibrium will be shifted to left. See, there are more number of CH3CO minus ions. So product concentration is more. According to Lee-Startley's principle, when the concentration of product increases, the equilibrium will shift towards left. Yes. Therefore, the dissociation of CH3COH will still get decreased. Will still get decreased, or you can say it gets suppressed. That is called what? That is called common ion effect. Yes. Then we have something called salt hydrolysis. what we mean by salt hydrolysis. And last will be buffer solutions. Okay. Salt hydrolysis. Salt, when it is treated with water, it hydrolyzes to give acids and bases. It is a reverse of neutralization reaction. So hydrolysis is a process which is reverse of neutralization reaction. So what we specifically say in salt hydrolysis is, specifically what we mentioned in salt hydrolysis is, it is the reaction of cation and anion, or both the ions of the salt with water, to produce either acidic or basic solution. To produce acidic or basic solution. Yes, that is nothing but salt hydrolysis. So hydrolysis is the reverse of neutralization. So you can see here, I can show you like this. Salt in presence of water, it will hydrolyze to give, it will form aqueous solution first. Aqueous solution. And that aqueous solution may be either acidic, it may be neutral, or it may be what? Basic. So when it is acidic, when we call it as cationic hydrolysis. Correct? Hydrolysis. When it is neutral, we call no hydrolysis. There is no hydrolysis taking place. Basic means anionic hydrolysis. Yes, anionic hydrolysis. So this is about salt hydrolysis. With this explanation, we have something called hydrolysis constant. See, if you consider a general reaction of hydrolysis of salt, let us say Ba plus H2O. So Ba is our salt, let me say. So this is my salt. It will dissociate to give me Ha plus BOH. So this is my acid and this is my base. You apply law of chemical equilibrium to it and tell me, you will get Kc will be equal to what? So I'll write it here. Ba plus H2O, it will give me a reversible reaction, Ha plus BOH. So by law of chemical equilibrium, dissociation constant is equal to what? Concentration of Ha into concentration of BOH divided by concentration of Ba into concentration of H2O. Correct? So this we called as equilibrium constant. Since water present is very large in excess, its concentration may be regarded as a constant. Therefore, when I take K that side, it becomes, I can write it as Kc into concentration of H2O, which is large in excess. I can write it as Ha into BOH divided by only Ba. Correct? So this and this constant makes another constant. I will write it as salt hydrolysis constant, represented as Kh. That will be equal to Ha into BOH divided by the salt Ba. Yes. So Kh is called hydrolysis constant. And if you want to find the degree of hydrolysis, yes, we have H is equal to number of moles of salt hydrolyzed. Yes, I'll take. It is the ratio of number of moles of salt hydrolyzed to total number of moles of salt taken. Total number of moles of salt taken. So this is what? H is what? Degree of hydrolysis. So with this explanation, you can find it for salt of strong acid and strong base. So first one. So I'll consider salt of, first let us consider weak acid. Okay, rather than wasting our time, we'll write it like this. Weak acid and strong base. If it is like this, then KH is equal to KW upon KA. and H is equal to root of KH upon C. KH upon C. Yes, and expression for pH is minus 1 by 2 log KW plus log Ka minus log C. Yes, this is the expressions. Second one, if you have a salt of strong acid and weak base, then KH is equal to KW divided by KB. H is equal to root of KH upon C, and pH is equal to minus half log of KW minus log of KB minus log of C plus log of C. Last one is salt of weak acid and weak base. KH is KW upon Ka into Kb. Dissociation constant is root of KH. pH is equal to minus half log of Ka plus log of Kw minus log of Kb. Last, if you see about salts of strong acids and strong base, do not undergo hydrolysis. They undergo ionization. Salts of strong acid and strong base undergo what? They undergo ionization. Therefore, they do not undergo hydrolysis. Therefore, we don't have all these. So they result in aqueous solution, which is neutral. Which is neutral. Is that clear? So this is about salt hydrolysis. Yes. So when you are carrying out all these things, no, we need indicators to indicate these acid-base titrations. That time we go across different examples. So if you have a strong acid versus strong base, strong acid versus strong base, you are carrying out titration, then the best indicator used is phenolphthalein. Phenolphthalein. Yes, if you are using weak acid versus strong base, still we go for phenolphthalein. Weak acid versus weak base, there is no indicator used. No indicator. Yes. So reason for the use of different indicators is indicators are either weak acids or weak bases. And when dissolved in water, their dissociated form acquires a color. So phenolphthalein color is what? It is colorless in acid solution. It is pink in basic solution. Yes. So therefore, they indicate different colors in acidic and basic solutions. That's the reason we go for what? We go for indicators to indicate the change in color when a reaction has occurred. Okay. So you can see here, hydrolysis of salts of strong acids and weak base. NH4Cl, yes, and NH4NO3. So hydrolysis, we get NH4OH, NH4 plus NO3 minus H2O gives NH4OH. Yes, after hydrolysis, solution will be acidic, pH will be less than 7. Since only cations of the salt participate in the hydrolysis, it is known as cationic hydrolysis. Hydrolysis of salts of strong base and weak acids. Strong base and weak acid. So here, what will happen? You will get CH3COH and OH minus ions. After hydrolysis, solution will be what? OH minus ions are there. It will be basic. pH will be more than 7. Only anions of the salt take part. Therefore, it is known as anionic hydrolysis. I have shown you. Cationic and anionic. Hydrolysis of weak acid and weak base. Weak acid, weak base. So pH of the solution depends upon relative strengths of the acids and bases. Yes. So this is about hydrolysis. And the last concept here is, so I have told you here only, you have seen in one of our slide we had discussed, which is cationic, which is here. Salt, aqueous solution. If it is acidic, cations have participated, therefore cationic hydrolysis. If it is basic, anions have participated, therefore it is anionic hydrolysis. Neutral, there is no hydrolysis. And if it is hydrolysis of a weak acid and weak base, it depends upon the relative strengths of acids and bases. Yes, and that is calculated with the formulae. Then the last thing what we are supposed to discuss is about the buffer solutions. So what do we mean by a buffer solution? the solutions which resist the change in pH on addition or dilution or with the addition of small amounts of acid or alkali are called buffer solutions. See, if you add, suppose you have a solution, if you add acid to it, the pH will decrease, correct? So when we speak about the pH scale, if I take it like this, so let me say this is my pH scale. Yes. So in this direction, so let me represent here. Here the value of pH is 7. Here it is 1 and here it is 14. Correct. So what does this scale represents? This represents acidic. Yes. How you move? As you move in this direction. Yes. What happens? What we call acidic strength increases. Acidic strength increases. Correct? Yes. And as you move in this direction, I can say acidic strength decreases. Yes, because pH I'm saying acidic strength decreases or basic strength increases. Correct? Yes, another way I can represent it as, if I say in this direction, what does it mean? It means that H plus ion concentration is increasing or OH minus ion concentration is decreasing. If I'm speaking in this direction, it means what? It means H plus ion concentration is decreasing or OH minus ion concentration is increasing. So suppose the solution is somewhere here, say pH is around 6. If I add for a solution of pH 6, it is what? It is acidic. If I add some amount of acid to it, what will happen? The pH will still decrease. It will be still less than 6. Suppose I have pH of 6, which is acidic. If I add some amount of base, what will happen? The pH will be more than 6. That means it will increase. It will become more than 6. Understanding? So here, what we understand is buffer solutions are those. What do we mean by buffer solutions is solution whose pH does not get altered even on addition of small amounts of either strong acid or strong base. They are called as buffer solutions. So it can be also defined as solution of reverse acidity or alkalinity, which resists the change of pH. Depending on that, we have types of buffer solutions. The first one is solutions of single substances. Solutions of single substances. Okay. So what do we mean by the solution of single substance? So solution of single substances means the solution of a salt of weak acid and a weak base. Salt of weak acid and weak base. So I can take acetic acid and ammonium hydroxide. Its salt is CH3CONH4 plus NH4. This is a solution of single substance. This can act as buffer solution. Even NH4CN can act as buffer solution. So this is first type. The second type is solutions of mixtures. Mixtures of acids and bases. Okay, in that we have two types again. We have acidic buffers and we have basic buffers. So acidic buffers means what? It is the solution of a mixture of weak acid and its salt of strong base. Yes, so weak acid, say CH3COOH, and its salt of strong base. So CH3COO Na. This is salt of strong base. This is what acidic buffer. Basic buffer means what? It is a solution of weak base and it's a salt of strong acid. Strong acid. Yes. For example, weak base is ammonium hydroxide and it's a salt of strong base is ammonium chloride. Ammonium chloride. Yes. So this is basic buffer, mixed buffers, right? So buffer action we have. What do we mean by buffer action? Buffer action is the mechanism by which the added H plus or OH minus ions are almost neutralized, so that pH practically remains constant. Practically the pH does not change, it remains constant. Yes, so that is called as buffer action. And to mention this, we have Henderson's equation. The last equation, yes, Henderson's equation for acidic buffers. For acidic buffers, I can write pH is equal to pKa plus log of concentration of salt to the log of concentration of acid. Yes, similarly, I can write when this becomes, when concentration of salt to concentration of acid is equal to 10, then pH will be equal to what? Will be equal to pKa plus 1 or 1 plus pKa. Yes. So for basic buffers, POH is equal to pKb plus log of salt by concentration of base. Concentration of base. Yes. So this is all about salt hydrolysis. Finally, what is buffer capacity? Buffer capacity, it is denoted as symbol this. It is nothing but number of moles of acid or base added, number of moles of acid or base added per liter to change in the pH. Change in pH. That is called as buffer capacity. Yes, greater the buffer capacity, greater is its capacity to resist the change of pH value. So as buffer capacity increases, it can resist, greater is the capacity to resist the change. And what is the significance of these buffer solutions? They are used for comparing colorimetrical of hydrogen ion concentration. Even acetic acid, sodium acetate, it is used in the removal of phosphate radicals during qualitative analysis of the mixture. There are many applications in biological systems also. Buffer solution of carbonic acid. What is carbonic acid? H2CO3 and sodium bicarbonate, NaHCO3. It is found in our blood. It maintains the pH of blood to constant value of about 7.4. Yes, in spite of various acid-base producing reactions going on in our body. This keeps our pH 7.4. So that is the buffer present in our blood, in our body. Carbonic acid and sodium bicarbonate. So this is all about buffer solutions. So you can see here which resist the change in pH, and here are the examples. Acidic buffers, pH is less than 7. Basic buffers, pH is more than 7. Solubility product, sparingly soluble salt. There exists equilibrium between ions and the unionized substance. For example, see, BaSO4 is there. You get Ba plus 2 and SO4 minus 2. We write the equilibrium constant as Ba plus 2 and SO4 minus 2 by concentration of BaSO4. Solubility product is nothing but what? Take concentration of BaSO4, this side becomes constant. That constant is called Ksp, and that is nothing but solubility product, like how you write ionic product of water. It is the product of molar concentrations of the ions present in that solution. Under equilibrium condition, Ksp is equal to Qsp. Yes, for a sparingly soluble salt, it is defined as the product of molar concentrations of the ions raised to the power equal to number of moles, number of times each ion occurs in the equation. So AgCl, Ag plus Cl minus, what is the solubility product? KSP is equal to concentration of Ag plus ions into concentration of Cl minus ions. Yes, so this is all about the topic of equilibrium, chemical equilibrium and ionic equilibrium. Hope you have followed with all the concepts. Yes, please practice all the concepts properly so that when we in the next class, we'll be dealing with the multiple choice questions. We are left with the last concept, that is Ostwald's dilution law, degree of dissociation. Yes, we have done it already. For a binary electrolyte, it dissociates to give A plus and B minus. For very weak electrolytes, dissociation is very less than 1. Therefore, 1 minus A is almost equal to 1. So I can write K is equal to C alpha square, or alpha is equal to root of Kc or Kv. So concentration of any ion is given by C alpha square or root of Kc or K by V. Degree of ionization increases on dilution. Thus, degree of dissociation of the weak electrolyte is directly proportional to the square root of dilution. And what is the limitation? It holds good only for weak electrolytes, but completely fails in case of the strong electrolytes. So this is all about the topic. Hope you have understood, got clear with all the concepts. In the next class, we'll be taking up the multiple choice questions on this topic. For now, thank you.